Hi friends, I am Snehal and today we are going to see what are free body diagrams and solving problems in mechanics using free body diagrams. So let's begin. So let's start with this simple problem. Two blocks of masses 6 kg and 3 kg are placed on a horizontal frictionless surface. If a force of 36 newtons is applied on mass m1, what is the force exerted by the string on m2? So there are these two blocks of masses m1 equals to 6 kg, m2 equals to 3 kg, and a force of 36 newtons is applied on m1. So question is, what is the force due to the string acting on m2? So we are going to solve this problem using free body diagram. So what is a free body diagram? So free body diagram is drawing one part of a system at a time or representing it by a point and then drawing all the forces acting on that part only. So let's consider this part or this block M2 and let's draw its free body diagram. So FBD of M2. So this is M2. Then what are forces acting on M2? One is obviously weight of M2 or the gravitational force which acts downwards and has magnitude equals to M2 times G. Then there is normal reaction due to this surface which acts upwards and balances the gravitational force. So normal reaction, let's call it N2. And then there is the force due to the string. So string is pulling M2 towards left. So let's call it tension in the string T. Now I can write down some equations here. For equilibrium in vertical direction, I can say that N2 equals to M2 times G. So normal reaction balances the weight. So we have N2 equals to M2 multiplied by G. Then there is no other force in horizontal direction. So we can say that this tension in the string causes some acceleration, and let's suppose the acceleration is A. So I can say that T equals to mass m2 multiplied by acceleration. Okay. So let's call this set of equations equation number 1. After that, let's draw a free body diagram of this mass m1. So FBD of m1 . This is mass m1. What are forces acting on it? Obviously there is weight of the block m1 times g. Then there is normal reaction which balances the weight. So let's call it n1. Then in horizontal direction, now there are two forces. One is the force exerted by some external agent F, and the other one is force due to the string. Now on this block M1, the tension will be towards right. Okay. Now I can write down some equations. So I have N1 equals to M1 multiplied by G. Normal reaction balances the weight. Then net force in horizontal direction . Let's call it small f or f suffix 1. This is mass 1. So f suffix 1 is equal to this force F minus tension in the string. Okay, this force acts towards left and tension acts towards right. So net force is subtraction of those two forces. So I can write F1 as mass of this block multiplied by the acceleration of the total system, which we consider to be A. So I can say that m1 times A is equal to F minus T. So I can call this equation number 2. Now what I can do is I can substitute equation number 1, specifically this equation, in equation number 2 to find out the acceleration. Okay, and after finding out acceleration, we can substitute that back into this equation to find out force exerted by the string on m2. Alright, so I will erase this part. So we have m1 times A equals to F minus T, and T is m2 times A. We can take this on the other side to get m1 times A plus m2 times A equals to F, and therefore we have A equals to, if we take A common, we are left with m1 plus m2. So we have A equals to F divided by m1 plus m2. Then we can substitute the values. So F is equal to 36, m1 is 6 kgs, m2 is 3 kgs. So if we substitute that, we have 6 plus 3, that is 9, and 36 divided by 9 is 4. So 4 meters per second squared is the acceleration of the system. So what is force due to the string acting on m2? So we just have to substitute this acceleration in this equation and we will get the force. So let's do that. So T, the force due to string on m2, is m2 times A, and A is 4. So m2 is 3. So 3 times 4, that is 12 newtons. So force due to string on m2 is 12 newtons. Alright, now let's see numerical number 2. So it's similar to the previous one, but I have changed one thing. I have added some friction into the problem. So now this surface is not frictionless. There is some kinetic friction, and the coefficient of kinetic friction is 0.5. And I have also changed the values of masses of these objects and also the force. Okay, so let's start again by drawing the free body diagram of this mass m2. So let's draw free body diagram of m2. So this is mass m2. Then what are forces acting on it? One is obviously the gravitational force or the weight, which is m2 times g. Then there is normal reaction acting upwards, which is n suffix 2. Then tension in the string, which pulls the block, T. And now when this block begins to slide, there is also some frictional force. Let's call it small f suffix 2. Okay. Now we can write down the equations. So normal reaction balances the gravitational force or the weight. So N2 is equal to m2 times g. But now net force in horizontal direction. So net force in horizontal, let me call it x direction. So this is x direction and this is y direction. So in x direction is, let's call it capital F2. Now it is equal to this tension minus the frictional force. So tension minus small f suffix 2. Now force is mass times acceleration, and frictional force is coefficient of kinetic friction multiplied by normal reaction. We can substitute that. So we get m2 times A is equal to tension minus mu k multiplied by normal reaction, and normal reaction N2 is m2 times G. So we get m2 times A is equal to T minus mu k multiplied by m2 times G. And if we take this on other side, we get tension. So tension is m2 times A plus mu k multiplied by m2 times G. So now I will call this my equation 1. Then next, let's draw a free body diagram of mass m1 or block of mass m1. So FBD of m1, so this is the mass, this is the external force F, gravitational force acting down m1 times G, normal reaction acting up n1, then there is tension in the string, so the string pulls m1 towards right, so tension in string, and also in addition to that now there is frictional force, so let's call it small f suffix 1. Now we can write down the equations. So normal reaction balances the gravitational force or weight, so N1 equals to m1 times G. Then what is the net force in horizontal direction? So net force in x direction now is, let's call it F suffix 1, capital F suffix 1. So the external force minus tension minus the frictional force. Alright. So external force is capital F minus tension minus this frictional force. Then we have found tension in the string, the formula for it. So we can substitute it, and also the frictional force is mu k multiplied by normal reaction, and normal reaction is m1 times G. So we can substitute all that to get capital F1 equals to external force F minus m2 times A plus mu k multiplied by m2 into G minus mu k multiplied by this normal reaction, which is equal to m1 times G. Now this F1 is the net force acting on this block whose mass is m1, so it is equal to mass of the block multiplied by acceleration. So I can note down this equation here. So F1, which is mass of the block m1 multiplied by A, acceleration. Then I can take this m2 times A on left hand side. So I have plus m2 times A is equal to F, and then I can take mu k common, G also common from these two terms. So I have minus of mu k times G, and I am left with m1 plus m2. So m1 plus m2. Let's check that. Okay, seems correct. Then I can take A common on left hand side. So I have m1 plus m2, I will take it to right. So it goes in denominator. So A is equal to F minus mu k times G multiplied by m1 plus m2 and all divided by m1 plus m2. Now I can substitute values of all the quantities to find out acceleration. Okay, so let's do that. So we have acceleration A equals to F, which is 150 newtons, minus mu k, which is 0.5, multiplied by G. So let's take it as 10, this acceleration due to gravity, multiplied by m1 plus m2, which is 10 plus 5, which is 15, divided by m1 plus m2, which is 15. So we have 150 minus 0.5 multiplied by 10 is 5. 15 5s are 75. So 150 minus 75 divided by 15, which is 75 divided by 15, so which is 5. So acceleration is 5 meters per second squared. Alright, and then finally we can take this acceleration, we can substitute it here and find out tension in the string, and which is equal to force due to the string acting on mass m2. Okay, so we have T equals to, I can take m2 common from these two terms, multiplied by A plus mu k into G. Then I can substitute the values. So m2 is 5 kgs, A we just found and it is 5 meters per second squared. So it is 5 plus mu k is 0.5 multiplied by G, and G we consider it to be 10. Okay, so we have 5 multiplied by 5 plus this 0.5 multiplied by 10 is also 5. So 5 plus 5 is 10, and 5 times 10 is 50. So tension in the string is 50 newtons. Now let's see numerical number 3, which is from NCERT. It's numerical number 5.16. It says two masses 8 kg and 12 kg are connected at the two ends of a light inextensible string that goes over a frictionless pulley. So these are two masses, m1 equals to 8 kg, m2 equals to 12 kg, and they are connected to each other by this string which goes over this pulley. Find the acceleration of the masses and tension in the string when masses are released. So when these masses are released, we have to find acceleration of these masses and also tension in the strings. Okay, so first thing that we are going to consider is the string is light. That means we are going to neglect the mass of the string, and it is given that the string is inextensible, so length of the string remains fixed. Okay, so that means tension in the string remains same everywhere in each and every part of the string. Then we have to consider one direction of acceleration, and this m2 is greater than m1. So we can expect that m2 will go downwards and m1 will move upwards, and acceleration is a. Okay, now we can draw free body diagrams of m1 and m2. So this kind of a system where there are masses connected with strings which goes over pulleys are called as Atwood's machines, and this is the simplest of an Atwood's machine. Okay, so let's draw free body diagrams of m1 and m2. So FBD of m1, so this is m1. Forces acting on m1 are the weight of m1 which acts downwards and tension in the string which acts upwards. So it is m1 times g, the weight, and tension, let's call it T, and we have considered the direction of acceleration as upwards for m1. So the net force is going to be in upwards direction. So therefore we can write net force, which is, we can say F1 is equal to upwards force, which is T, minus downwards force, which is m1 times g. So F1 is m1 times A, which is equal to T minus m1 into g. And if we take m1 times g on the other side, we get T equals to m1 times A plus m1 times g. And I can call this equation number 1. Similarly, I can draw free body diagram of mass m2. So this is m2. Weight acts downwards, which is m2 times g. Tension acts upwards, which is T. And the direction of acceleration is downwards. So net force is going to be in downwards direction. So I can say net force on this mass m2 is equal to m2 into g minus t. So net force, let's call it F2. It is equal to m2 times g minus T, tension in the string. Then F2, I can write this as m2 times A, and it is equal to m2 times g minus T, and this is my equation number 2. Then I can substitute this tension in the string from equation number 1 in equation number 2 to find out acceleration. So let's do that. So I have from equation 1 m2 times A is equal to m2 times g minus m1 times A plus m1 times g. So I can take m1 times A on the other side. So I have m2 plus m1 times A. Okay, if I take this on the other side, it becomes m1 times A, and from m2 times A and m1 times A, I can take A common. So I'm left with m2 plus m1. And on right hand side, I have m2 times g minus m1 times g. So I can take g common. So I'm left with m2 minus m1 multiplied by g. Okay. Then A equals to, I get m2 minus m1 divided by m2 plus m1 multiplied by g. Okay, and we can check whether our considered direction is correct or not. So m2 is greater than m1, that means this numerator is going to be positive, that means acceleration is going to be positive, and therefore the direction that we have considered for A as A in downwards direction, it's correct. Okay, and finally let's put the values of all these quantities to find out acceleration and tension in numbers. So we have A equals to m2 minus m1, so which is 12 minus 8 divided by m2 plus m1, which is 12 plus 8 multiplied by g. So let's consider g as 10 meters per second squared. So in numerator we have 4, in denominator we have 20 multiplied by 10. So 20 by 10 is 2 and 4 divided by 2 is 2. So we get acceleration as 2 meters per second squared. Okay, and then tension is equal to m1 times A plus m1 times g. So tension in both the strings is m1 times A plus m1 times G, which is equal to m1 is 8 kg multiplied by 2 plus 8 multiplied by G is 10. So 10 8s are 80, 80 plus 16, which is I guess 96 newtons. Okay, so tension in strings is 96 newtons.